Okay, imagine for a second that you could build the future. Not with a hammer and anvil, but with a beam of light and a cloud of metal dust. Well, that's basically what we're talking about today, 3D printing with metal. It's a technology that is literally reshaping our world, one tiny molten layer at a time. So let's dive into this quest for manufacturing perfection and see how researchers are taming liquid metal. So, what can you actually do with this kind of technology? I mean, what's the big deal? Well, the applications are pretty much straight out of science fiction, but they are very, very real. For starters, think about the inside of a jet engine. We're talking about some of the most extreme conditions imaginable: insane heat, incredible stress. With metal 3D printing, engineers can build these unbelievably complex parts, like turbine blades that have cooling channels running right through them. This makes engines lighter, stronger, and way more efficient. It's an absolute game changer for the aerospace industry. Or, hey, let's switch gears to the world of medicine. This exact same technology can create custom-fit medical implants, perfectly sculpted to a single patient's body. And, this isn't just about making things more comfortable. It's a huge leap forward in medical science. We're talking stronger, better integrated implants that can genuinely change people's lives. So the magic behind all this has a name: Laser Direct Metal Deposition, or LDMD. Now, I know that sounds super technical, but the idea is actually pretty simple. Picture a nozzle spraying this really fine stream of metal powder. At the exact same time, a high-powered laser is melting that powder right onto a surface. The best way to think of it, it's like a hyper-precise, laser-powered glue gun for metal, building something real from the ground up, one microscopic layer at a time. But, like any really powerful technology, it's not perfect. It's got its challenges. And that brings us right to the heart of our story today, a specific problem that a team of researchers decided to tackle, and they focused on one particularly tricky and very expensive material. The number one challenge is something called powder catchment efficiency, or PCE. It's a really simple metric, but it is absolutely crucial. Basically, it asks, of all the metal powder you spray out of the nozzle, how much of it actually becomes part of the final product. Getting this number right is the key to making the whole process efficient and, affordable. So in the industry right now, a PCE between 40 and 65% is considered noticeably good. Just let that sink in for a second. Even at its best, that means over a third of your super expensive high-tech metal powder is just gone, wasted. So yeah, there's a massive opportunity for improvement here. Here's a really simple way to picture the problem. On the one hand, you have all the powder you deliver, the total amount you're spraying. And on the other, you have the much smaller amount that actually gets captured and fused into the part. That gap between the two, well, that's just wasted material, wasted energy, and a whole lot of wasted money. All right, so let's meet the main character of this story, a material called Stelcar 65. Now, this is not your everyday metal. It's a super alloy, a special mix of nickel and tungsten-carbide. It is incredibly tough, it can handle extreme heat, which is exactly why it's used in things like jet engine parts and heavy-duty industrial drills. And, as you can probably guess, it is very expensive to waste. So the mission was pretty clear. Figure out the most efficient way possible to print with Stelcar 65. And this wasn't about just guessing and checking. This was a full-on scientific quest to find the perfect recipe for manufacturing. But that brings up a really important question, right? When you're juggling all these different variables, the heat of the laser, the speed, the material flow, how on earth do you find that one perfect combination without wasting tons of time and even more of that pricey powder on trial and error? Well, the answer is you do it with science. The researchers use this really powerful statistical method. We can break it down into 4 basic steps. First, they figured out what the most important variables were. Second, they designed a whole series of really careful, controlled experiments. Third, they took all the data from those experiments and used it to build a predictive mathematical model. And finally, they used that model to zero in on the single best combination of settings. For this particular study, they boiled it down to the 2 most critical variables. First up was laser power. How hot does the laser actually get? And second was scanning speed. How fast does the laser head move across the surface? They knew that the secret was hidden somewhere in the relationship between these two. So after all that planning, all the experiments, and all the modeling, it was finally time for the big reveal. The data held the answer, that optimal recipe they had been searching for. So how'd they find it? By plotting all their results in 3D, a really clear picture started to emerge. It looked kind of like a mountain peak rising out of the data, a sweet spot where one specific combination of high laser power and low scanning speed created the absolute best results. And here it is, the winning combination. The perfect recipe for Stelcar 65 turned out to be a laser power of 1850 watts paired with a scanning speed of 7 millimeters per second. That precise combo, that was the peak of their mountain. So what did this brand new recipe actually achieve? A powder catchment efficiency of 69.08%. Now remember, the industry standard for good maxed out at 65%. This was a really significant jump forward, setting a whole new benchmark for how to do this efficiently. And get this, because this is what really shows you how powerful their scientific method was. That predictive model they built, it was 98.52% accurate when compared to the real-world experimental results. That is an incredibly reliable model, which gives manufacturers a ton of confidence that these results can be achieved again and again. But the research gave them more than just a set of numbers. It gave them a much deeper understanding of the process. They discovered that even though both variables mattered, the scanning speed actually had a bigger impact on efficiency than the laser power did. Turns out, a slower speed just gives the powder more time to melt thoroughly and bond properly, and that was the most critical factor of all. Okay, so a breakthrough in a lab is one thing. That's fantastic. But the real test is how this kind of research actually translates into real-world impact for industries and, ultimately, for all of us. The benefits here are really clear and they're profound. For one, less waste means lower costs, which makes these amazing high-performance parts more affordable. It also means you get stronger, higher quality parts because the whole process is just more controlled. And by using less material and less energy, it makes the entire manufacturing process way more sustainable. So we have to ask the final question. Why does a small efficiency gain on some factory floor actually matter to you and me? Well, it matters because it means the next plane you fly in could have parts that are lighter, stronger, and safer. It means the tools that build our cities and our homes can be more durable and more efficient. This is exactly how fundamental research pushes our entire world forward. This is how you bridge that gap. You take a really complex problem, you apply rigorous science, and you create a solution that makes a real, tangible difference. It's just a powerful reminder of that critical link between pure research and real-world impact.